All right. This is page 54. We're looking at the different characteristics of a quadratic function. Like I said, we are in Unit 4, which deals with quadratics. Quadratics are this blue curve that you see here. If you want to take your colored pen or highlighter, since there are a lot of arrows here, you probably wouldn't be a bad idea to highlight the blue parabola that you see on the board. Okay, first of all, a quadratic is a function that can be written in the form, and then this is blank right here. Notice it says standard form. What's the most standard way to organize a bunch of things? How would you organize like a set of books? If you had a set of books, how would you organize them? Well, I mean, like, how would you rearrange them?
Size.
In order of what? Like, what type of order?
Letters.
What letter? Like, what comes to mind?
Alphabetical order.
Alphabetical order. You see how I tried to get you to say that a standard form is alphabetical order? Look at this. Come on, please work. AX squared plus BX plus C. Notice the ABC order, and then, of course, equals 0. That is standard form of a quadratic.
Were we supposed to write this?
If I'm writing, you're writing.
Right in the same spot you write.
Yeah. It should be up there at the top. You should see a line. How do we know it's a quadratic? Do you remember what lets me know this equation is a quadratic? It has to do with the degree.
Oh, the degree?
Yes.
Degree 2.
This 2 right here is what lets me know it's a quadratic. So if you need to refresh your memory, a quadratic function. Quadratic means degree 2. That's how you know it's a quadratic. This is a quadratic. F of x equals x squared minus 2x minus 3. Now, this f of x, it's been since Unit 1 that you've seen this. The way you read it is the phrase f of x. That means the name of the function's f, your input variable's x. Your output variable is f of x. This is your output, okay? So it's like a vending machine. If I plug money in, food or drink comes out, right? I'm going to plug x in, type it all in my calculator, and then I'm going to get a number out. Input x, output y. But because it's a function, we call it f of x. I want you to tell me right here in these 3 boxes, what is the number for A, B, and C from this example right here. I want you to write the coefficient A, B, and then the constant C. Everybody try it. Here's what we were talking about earlier. If you're not actively trying the problems before I put it on the board, you're not actually running the play, okay? So make sure you're actually trying when I say, hey, you try real quick. Braxton, stay with me. So the only one that's probably tricky would be A, and that's because there's no number here. What number is understood to be here? There's a positive 1 here. What's B? Negative 2. Watch your signs. And what's C? Negative 3. Now, the graph of a quadratic equation creates a U-shaped curve that we call a parabola. No, it's not parabola. That sounds like a virus. It's parabola. That's just another word for it. This blue curve that you highlighted is a parabola. There's a couple of characteristics involved with parabolas, with quadratics, which is what makes them really neat when you're studying. Okay, I use the word neat loosely, sorry. Basically, every parabola that you work with is either going to face up or it's going to face down. Don't highlight that. That's right. Yeah, you're good. It's either going to face up or it's going to face down. You're never going to have a parabola turned like on its side. And there's a reason for that. This f means it's a function. If I have a graph turned on its side, do you it's wait, you're so close. Do you remember that?
Oh, I know what it is.
Yes.
What is it? No, it's like constant.
Kind or be quiet. How about vertical line test? Thank you. This would fail the vertical line test passing in multiple places. That's why you'll never have a parabola on its side. They're always going to be up or down. Now, how do you know which way it's facing?
Positive, negative.
This is why I love math. It's common sense. What do you think positive would open?
Upward.
Up. And what do you think negative would open? Down.
Downward.
Now, where's the positive negative actually going to be? It's going to be with this number right here. Okay? If A is positive, then the parabola will open up. And if A is, where do you think I'm going? Negative, then the parabola will open down. Simple enough. If A is positive, I didn't mean to leave that highlighted. If A is positive, it opens up. If A is negative, it opens down. Simple and easy. Now, couple of boxes here. Do you happen to remember, if you have a different color, it would really help. Do you remember what these points are called where the graph is crossing this x-axis? Yes. These are your x-intercepts. These are your x-intercepts. Now, there were a bunch of other words for it. We're going to come over here to this box. They were also called roots. They were also called zeros. And they were also called solutions. Now, don't ask me why, but for some reason, there are 4 different words to mean the exact same thing. 4 different words. It's a little overkill, I agree. But some of them are common sense. X-intercepts. It's where the graph is intercepting the x-axis, which happens to be the solution to any equation, which is where that hack comes in that I showed y'all on Desmos. If you just type it in Desmos and you look at where it's crossing the x-axis, bam, you have your solutions every time. Granted, sometimes they're ugly decimals and they want radical form, not decimal form. Zeros is a word that is given to it because when you're looking at the x-intercepts, it's kind of like where it's like ground zero. You know what I mean? Have y'all ever heard of ground zero? Ground zero is obviously where in New York City, or neutral, you could say. But it's kind of like, it's like this. Help me out. I'm trying to think of how to describe it. It's like the key focus, like like everyone's focus and attention is right there at ground zero. This is where all the activity's happening, right? Roots. Watch this. I want you to think of a tree. You don't have to draw this. I want you to think of a tree. Yeah, I'm trying to color it. All right. Anyways, and then you have the ground, right? All right. Where do a tree's roots grow? In the ground, right? Where does the root first touch the ground? Right here. Do you kind of see the whole concept of like a quadratic?
No.
And this is the x-axis. And the root.
Oh, and those are your x-intercepts.
And those are your x-intercepts. Now, granted, there's no tree picture here, but I want you to think of like this. This is the ground, right? And then like this is the sky. Yes. Okay, and then you have some tree, weird tree. And this is where the roots are touching the ground. Okay? So there's your visual to remember the word roots, because you may be asked, what are the roots of the quadratic function? And you'll be like, what roots? What's a root? I want you to think of that visual of the tree growing in the ground. Like, where's it crossing the x-axis?
Do they ever like try to trick us like the way you word it? Like often on the test?
Oh, I don't know about that, but it wouldn't surprise me. You're supposed to know all those words. Now, what do you think? Keeping in mind what an x-intercept is, right? Keeping in mind, I want you to put your pencil on this graph where you think the y-intercept is. Put your pencil on the graph where you think the y-intercept is. Everyone should have their pencil in a spot. You've actively thought this through. Your pencil's supposed to be on your paper where you think the y-intercept is. Did you put it right here? All right, just make that point a little bolder, and then let's label it. That is our y-intercept. I definitely want it to be in a different color. This is our y-intercept. What if I didn't have the graph? What if I just had the equation? So here's another equation. This is not this graph. What do you notice about the y-intercept? Like, what are the let's get there together. What are the coordinate points of this? In your head, I want you to think of what's the coordinates of this point right here. In your head. Wait a minute. In your head. The coordinates of this point. 0, -3. Yeah, 0, -3. Okay, now let's just pretend. What if the x-intercept was, say, like here? Don't actually draw that. What if it was right there? What would the coordinates? 0, 2. All right, what about here? 0, -4. What about here? What about here? What do you notice is the same in every answer?
0.
For which value? The y-intercept can be easily found by simply plugging x equals 0 in, because it's going to land on the y-axis. Well, what's the x value on the y-axis for every point? 0. So this y-intercept, all you have to do is plug x equals 0 in to get the y-intercept. Now, the beautiful thing is you don't even have to go to your calculator, because what happens when you plug 0 in this? Think about it. 0 squared. 0. -6 times 0. 0. This is why 0 is so beautiful. So what happens to all this when I plug 0 in? It is gone. Now, what's the only thing left, though? And that's C, right? So when you plug x equals 0 in, you're going to be left with just the C value. So in this case, the y-intercept of this would be 0, 5. I didn't even have to type it in my calculator, didn't have to type it in Desmos, didn't have to graph it. What do you think this point is called? Notice where it is on the curve. It is in the middle. I want you to look at the rest of the vocab words on this paper and tell me what you think this point is. What? Or max or min? Which one do you think this is? What makes you think it's a minimum? It's bottom. No, okay, now that's a great point. I'm so glad y'all said that. I never thought to discuss that. What if the curve looked like this? So now it's positive. Is it still a minimum? You said it was a minimum because it was like down here in the negatives. What if it's one of these scenarios? Is this still a minimum?
Yeah.
How?
That's a great question.
Wait.
You're not understanding.
Wait a minute. Hold on. He's getting there. You're comparing it to the graph, like the grid. I want you to think about it in terms of just the curve itself. Just look at the curve. Don't worry about the grid. Where is it on the curve? So if your focus is only this curve, where is it?
The bottom.
Oh, it's at the
What
bottom.
is the bottom?
The bottom implies minimum. It's bottoming out.
Oh, boy!
See, you got there. You got there. All right, so the bottom is implied, like minimum implies it's bottoming out, like this is our lowest point. What direction do you think the curve needs to face for a maximum? It needs to face downwards,
Wait, so the point's at the top.
which means it's topping off, right?
Yeah.
So like if we have a curve like this, and this is the maximum. Okay, so let's come over here. Now this particular example, though, we already said is our minimum. Now, this example has a minimum, and you always want to read the y value here. It has a minimum, read the y value, -4, has a minimum of -4 at, what's the x value there?
What did you just write? -4.
It has a minimum of y equals -4, and it's at the x value of 1. It's a backwards way of writing the coordinate point. What is the coordinate point here? It's 1, -4. Well, if I want to discuss it as a minimum, I basically have to say, okay, it's a -4, where? At x equals 1. Okay? This is new. What do you notice about the yellow dotted line? Notice where it's placed. It is vertical.
In the middle of the.
Is it in the middle? Everybody look.
No, it's at the.
In the middle of the parabola. There's a math word that starts with S. S. You're fine. Starts with S
Subtract.
that works with when something is in the middle. There's a math word.
What's the second letter? This Tom?
No, I don't want to take the second letter. Listen. Symmetry. This is our axis of symmetry. This is our axis of symmetry. If you don't know how to spell it, it's on your paper right here. The axis of symmetry splits the parabola right down the middle. Right down the middle. How far is this right here from that x-intercept to the right? 2. How far is it to the one on the left? 2. It's always equidistant, okay? And it always passes through your vertex. This is actually called the vertex. We wrote minimum there. You really could have put, we could have put 2.
The other way would be 19.
Yeah. Let's call it the vertex. Oh, shoot. Let's just draw an arrow right there and come right here and we'll say this is also your vertex. Your vertex always serves as the max or the min. It's the center point. Okay? All right, let's fill all this in. So, what is the vertex? It is the point. Come on. It's the point in the middle of the parabola. What is the vertex in this example? We said it's 1, -4. What is your axis of symmetry? It is the vertical line that divides the parabola into 2 equal parts. The equation of the axis of symmetry, Braxton, stay with me. The equation of the axis of symmetry. Do y'all remember Hoy-Vux? If you had me, I'm going to write it right here. Hoy-Vux. It's a vertical line. You don't remember it? It means vertical lines. I don't want to write it all out. We'll write it on another paper. It's going to get crowded. The equation of all vertical lines equals x equals the x-intercept. What is the x value of the vertex? 1. So guess what? The axis of symmetry's equation is x equals 1. Because it's passing right through the vertex. Notice right here. There's a 1. This is a vertical line. So x equals 1. That is your equation of the line. We need to make a note. This is your equation. This is not saying, hey, I solved it. X equals 1. No, 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 no. That's an equation of a line. Now, we already said if it has a max or a min, it depends on which direction it's opening. This would have a max, and this would have a min. Now, remember, it's always the y value at the given x value, okay? Domain, range, increasing, decreasing, intervals, and in behavior. Let's do the in behavior is not bad. We'll do that one. Domain, range, increasing and decreasing. I'm going to save that to be able to go over with you when I feel like you've not been shoved with all this other information. In behavior is a fancy way of saying, what's the graph doing at the end of it? Well, didn't we say that the graph only faces one of 2 possible ways? We said it's either opening down or it's opening up, right? Okay, so that makes this really simple. Now, all this fancy stuff, let me zoom in because it's really small right here. All this fancy stuff, let me explain this. This is referring to this picture, and this is referring to that. Do you notice they match? Okay, so this is all kind of like a template, meaning this is the same every time. What changes is the very last part. All you have to do is ask yourself, what direction is the curve going? Is it going up or down? What type of infinity goes up? Positive. What type of infinity goes down? Negative. So right here, this is going down towards negative infinity, which tells me, now here's how you read it. Watch. Very sophisticated. As x goes left, because left is this way, right? As x goes left, the graph goes down. As x goes right, the graph still goes down because it's opening down. These should match, by the way. If they don't match, you've done something wrong. Might want to make a note of that. They should match. Your graph has what's called the same in behavior, meaning both arrows are going the same way. So your in behavior should match every time. Now, here we go. What's this one doing? It's going up. So as I read the graph to the left, it goes up. As I read the graph to the right, it's also going up. So you might want to make a note, should match. They're never going to be opposite. Should match. Now, I feel like I've given you enough new stuff and some stuff that's from last semester that you should be able to do an assignment like where you're starting to put it together.
I got questions though.
Yes.
Can I go to your direction?
Yes.
I'll tell.
Let's do this. I'm going to give you a 5-question, might be 7. I need to see how many topics are there.
Hey, you're so
Oh, I am, Lorna.
I don't even have that picture.